So now the lecture will be recorded. So what is on our agenda today? I would like to talk about a paper of Lazear and Rosen, published in 1981, and it's about rank order tournaments. And I would like to motivate this talk by looking at this picture. It's the finish of a marathon. So these two athletes have already run like 42 kilometers. And after 42 kilometers, it's a case that these two athletes are relatively close to each other. One person will win this competition. So it seems to be the case that this lady here in the middle is winning this competition. And the lady to the right, she's on the second place. And the winner will receive a very, very high prize money. And the prize money for the second person is relatively lower. Despite the fact that the effort level seems to be almost identical, like the two athletes, they excelled the same effort in this competition. One person will get a very high prize money, and prize money for the second person is lower. Big question is why? Is this optimal? What is the optimal staggering of prize money in such a competition? The overall underlying assumption is that the sports organizer who is organizing this competition is a principal, and the two athletes are the agents. So once more, unlike we have a principal-agent conflict, as you get to know in the lecture of Banti. But the special element here is that we have two agents and not only one. But like the overall idea of an agent and how the agent behaved, this is identical to the lecture of Banti. Like in itself, we always assume that the agent is very lazy. In case that we don't come up with the optimal contract, the effort level chosen by the athlete will be relatively low. So we need to design the right contract in order to motivate the agent. The agent is not motivated by himself or herself. This is the very basic underlying assumption of like this principal agent models. Yeah. Let's come up with one numerical example also in the motivation of this lecture. Let's assume that in one scenario we have an overall prize money of 1,000 euro, and 500 goes to the first place and 500 goes to the second place. So the overall prize money is, or like we call it also the purse, like W1 plus W2. The sum of the prize money is equal to 1,000, but the difference is equal to 0. Compared to scenario B, where the prize money for the first place is 70, prize money for the second place is 30. The purse, the sum of the prize money is equal to 100, and the difference between the first place and the second place is equal to 40. Now, the big question to the audience, like in which scenario do we observe like a more intense competition? In which scenario is the effort level higher, and why is that the case? Somebody would like to answer? Else, I stop the video signal, start a videotaping once more, and we'll proceed with the structure of the industry. Structure of the industry as follows. The spectator will pay the firm, and the firm is a tournament organizer. Afterwards, the firm, like the tournament organizer, will pay the workers, will pay the athletes, and afterwards the athletes will excel effort and will create output, and the firm will sell the output to the spectator. The background of this paper is that it is a labor market paper, and the overall question which is asked and answered in this paper is how to best compensate workers. Should worker receive a hourly wage, or should workers receive a piece rate pay? Piece rate pay implies, like Akkordlohn in German, workers are only compensated for the amount of output. Big question, like how does the principal get the best effort from the agents? Hourly wages, piece rate pay, or what if the principal sets up a competition? The more successful agent should receive wage rate 1, the less successful agent should receive wage rate 2. Of course, it has to be the case that W1 is larger than W2. The prize money for the first place should be larger than the prize money for the second place. Furthermore, we have the following assumptions: one-shot game, no repetition. And this rules out, like, all the arguments with respect to reputation, that the athletes have to build up reputation, that these athletes are always competing on the best level they can. This argument is ruled out here. So two agents, like workers, competitors, or athletes, are competing for first and second place. The firm organizes the tournament, and the principal and the agents are risk neutral. In the next part, I will talk about what happens if the compensation is a piece rate compensation. So this is the basic scenario, like piece rate compensation, Akkordlohn. This is the basic scenario. And then we compare the piece rate scenario with the competition scenario. We are looking at two workers. The workers are indexed with the index I, and the two workers are J and K. They produce an output QI by applying effort MI. More effort will lead to higher output, but the process is disturbed by an error term epsilon I. So QI is the output, MI is the effort level, and epsilon I is the error term. Normally, one worker can produce 1 unit of output per day. So when the effort level MI is equal to 1, then we can get 1 unit of output per day. But sometimes the worker is in a flow and can produce more. And sometimes the worker has a hangover and can produce less. This implies that on good days, epsilon I is positive. On bad, and then the output will be higher. On bad days, epsilon I will be negative, and the output will be lower than 1. And on normal days, epsilon I is equal to 0. And on normal days, the output will be equal to 1. We assume that the effort level MI as well as the error term epsilon I are unobservable. The firm and the spectator can only observe the output level QI. So, like on this race day, we can only observe like how fast these athletes are running. We cannot observe whether they put a lot of effort in their training exercises, whether they stick to a healthy diet. This is all unobservable. We only can observe the output, the time one athlete is running. Supplying of effort is costly for the agent. When one individual is running, this goes hand in hand with some costs. And these costs are modeled by a cost function, Cm, which has the following characteristics. First, C prime, the derivative of the cost function with respect to the effort level should be larger than 0, should be positive. A higher effort level will lead to higher cost. Furthermore, the second derivative should also be positive, which implies that marginal cost increase. In a marathon, it is the case that the athlete has to run from kilometer 8 to kilometer 9. And the athlete also has to run from kilometer 38 to kilometer 39. So the athlete has to excel some effort to run this 1 kilometer. Which kilometer comes along with a higher cost level? Of course, in the second scenario, in the second example, because then it is the case that already more kilometers were run, and therefore the next kilometer will come along with higher cost. So C prime is positive and C double prime is also positive. Here we have one cost function as one example. Cm is equal to m to the power of 1.5, and we can check whether this cost function fulfills the criteria mentioned above. So let's compute C prime. Del C del m is equal to, we take the exponent, write the exponent in front of the expression, and reduce the exponent by 1 unit. So we get 1.5 times m to the power of 0.5, which is positive. And then we can also check the second assumption. Is the second derivative del squared c del m squared positive? So we have to differentiate the first derivative once more. So we take this exponent here, write the exponent in front of the expression, and reduce this exponent by 1 unit. And we get 1.5 times 0.5, and then 1 over m to the power of 0.5. This is also positive. So this function, which I've just introduced here, fulfills the criteria mentioned above. The worker. The company pays the worker a piece rate equal to R. The expected earnings of each worker are equal to R. This is like the rate. Q is the output. So R times Q, these are the revenues. And then we have to subtract the cost. It is the case that we assume that the epsilons have a normal distribution, and expected value of this epsilon is equal to 0. Therefore, the expected utility becomes R times M. These are like the revenues from excelling this effort level, and then we subtract the cost. So the first order condition becomes, we are differentiating the utility function with respect to M, and we get R minus C prime. This has to be set equal to 0. So that in the equilibrium, it is a case that the rate is equal to the marginal cost. The rate paid to the worker is equal to the marginal cost. We also have to check what's going on with the firm. The firm will sell the output to their customer at a price of V. This is the spectator. And the cost of the firm is given by the labor cost, R times Q. Therefore, the profit function for the company is given by V times Q. These are the revenues, and R times Q. These are the cost for the company. When we put Q out of brackets, then we get V minus R times Q for the profit function. We assume that the firm operates in the market structure of perfect competition, so that profits are equal to 0 in the long run. And this implies that the profit margin has to be equal to 0. V minus R can be interpreted as the profit margin. And when the profit margin is equal to 0, then V has to be equal to R. When we now also take into consideration the optimality condition for the athlete, the optimality condition for the worker, then it becomes clear that V is equal to R is equal to the marginal cost of the worker. And hence, we have shown here that piece rate work is socially optimal. It is efficient. So piece rate compensation is efficient to the society which we have modeled here. This is the setup, the basic setup in the beginning of this Lazear-Rosen paper, that we look at the piece rate scenario. What you have to remember is the cost function is very important. What is also important is the market structure the tournament organizer is operating in. It is the market structure of perfect competition, so that the tournament organizer is not able to generate a profit in the long run. Any questions so far? Else, let's proceed. Now we are switching to the scenario where we look at the tournament. Let's have a look at the worker. With a probability P, agent J is better than agent K and receives the high wage rate W1. And with the counter probability of 1 minus P, agent J is worse than agent K and receives a lower wage rate W2. So the utility for a worker is given by probability of becoming number 1 and receiving the high wage rate, plus 1 minus the probability to be number 1 times the lower wage rate, and then we subtract the cost. Now we can write P out of brackets, like we have a P here and a P there. So we get P times W1 minus W2 plus W2 minus CM. This is the utility for the worker. We'll come back to the utility function later on. Now, I would like to talk about the probability function. How does this probability function look like? We have to think about the relationship of the output of QJ and QK and agent K, because this will determine whether agent J wins or whether agent K wins. So whether agent J wins the tournament or not depends on the relationship between the output of agent J and agent K. The output depends on the effort level as well as the luck component. So for QJ, it is the case that the output depends on the effort level, MJ, plus the luck component, epsilon J. Therefore, when we insert this kind of stuff for agent J and also for agent K, we know that agent J will win this competition in case that his output, which is given by the effort level plus the luck component, is larger than the corresponding elements for agent K. We can write this MK on the other side of the inequality and EJ on the right-hand side of the inequality. And then we get in equation number 9, we have on the left-hand side of the inequality the difference between effort level of agent J and the effort level of agent K. So the effort differential is on the left-hand side. And on the right-hand side, we have the difference between the luck components. So in case that EK is larger than EJ, then the luck component is in favor of agent K. So like a positive error term is good. A positive error term will lead to higher output. Okay, let's proceed with this probability function. Lazear, Rosen, they define the difference between the two shock components as Xi, EK epsilon K minus epsilon J. And Maloney, in one paper which I also uploaded, he uses the variable X in order to define the difference between these two luck components. And he comes up with a special label for this variable. And he calls this variable X the density of bad luck. I like this kind of label for this difference. And of course, I would like to know, like, bad luck for whom? It is the bad luck for player J. Because when there is a high epsilon K, the output of agent K will be relatively high. And this will influence the likelihood to win the competition for player K, and hence, like a high epsilon K will be bad luck for player J. How can player J win the competition? Player J can win the competition in case that the effort differential is larger than the realized bad luck component. So when the agent J has bad luck and the luck component for K is larger than the luck component for agent J can still win the competition in case that he has put more effort into the process. In case that MJ minus MK is larger than the realized bad luck component. When you look into the paper of here Maloney 2003, you find this figure, the probability of winning. I also like this figure a lot because it demonstrates more or less what's going on. So let's define first what is displayed on the two axes. On the horizontal axis, we have the difference between epsilon K and epsilon J. So on the horizontal axis, we have the difference between the two luck components. And in case that we are to the right of 0, then the bad luck component is positive, and epsilon K is larger than epsilon J, and it is bad luck to agent J. When we are to the left of the origin, which is labeled as good luck, then epsilon k is smaller than epsilon j, or putting it the other way around, epsilon j is larger than epsilon k, and we have like a relatively high positive error term epsilon j, and this is good luck for epsilon j. This is also mentioned like in the upper part of the figure. In the upper part of the figure, like we have displayed this kind of line of argumentation like in formal terms. And then or like we assume that this is normally distributed, like this bad luck, good luck is normally distributed, as you can see by the shape of this probability function. Then you also have a line, and it says extra effort by J. So it seems to be the case that in this graph, one situation is depicted where MJ is larger than MK. The difference between the two effort level is positive. Agent J is excelling like a larger effort level than athlete K. And due to the fact that agent J is excelling a larger effort level, the probability is not 50-50, but the probability for agent J, the winning probability is higher. So 50-50 would mean we are here in the middle of this distribution, but this second vertical line is to the right, and therefore maybe the probability for agent J is 75% to win the first place, because agent J was excelling like a higher effort level. Is this vertical line in the end important? No, the vertical line, which is labeled by extra effort by J, is not important. At least the position of this line is not important. It is not important because we will model the two athletes in a way that the two athletes are the same. The two athletes are symmetric. And therefore, in the equilibrium, it will also be the case that the two athletes will excel the same effort level. And when they excel the same effort level, then the difference in effort will be equal to 0. So what is important in the end is the vertical line which goes like through the origin. This is very important. And let's make another point by looking at this figure. What if we let this step which goes to the right, like this extra effort level by J, when we let this J, when we let this extra step and the step size to the right, when we let this step size converge to 0, how much probability does agent J add in case that he goes this very small step to the right? Like here in the graph, it is the case that the extra effort level by agent J is a big step to the right. And therefore, when this agent J goes this extra step, then he can add a lot of probability to his winning probability. It's like 25%. As we said, like left to the 0, this is 50%. The second black area, this is 25%. And the white area to the right of this vertical line, this is also 25%. But when we let this step to the right converge to 0, then how much probability is agent J adding? This is given by the height of this probability function. So when the distribution is very, how do you say, skewness kurtosis, when it has a low kurtosis, then it is the case that this density will be very high. And when we go then one step to the right, then this athlete is able to add a lot of probability because of the fact that the density is very high. But when the volatility is relatively broad, then we cannot add that much volatility. I don't know whether this became clear, and therefore let's try to add one file. And I hope that it makes it a little bit more clear. Okay. I hope that you can see now like a red line. And when we go like to the right from the origin, one step, how much probability do we add? It is like this distance here. Let's add another normal distribution. And this normal distribution has like a higher variance, like this. What happens when we go like one step, or when player J goes one step to the right, like player J can add like this amount of probability. So what is very important here is that the variability of these luck components decide in the end about the height of this density function at the origin. And the only stuff which is important is like the height of this density function. This is like one element which will be important later on in this numerical example, but also in the theoretical solution. Like the height of the density function will become one important parameter. I'll stop the presentation here. Then I will proceed. Go back to this presentation here. Okay, now you should once more see the presentation. So once more, it is explained here what is displayed in this graph. So in case that player J pushes its effort level above the effort level of player K, then MJ is larger than MK, and player J can still win despite some portion of bad luck, and player J can increase the winning probability above 50%. So here maybe it will be about 75% winning probability for player J because of the fact that he excels a higher effort level than player K. But like in 2 slides, as I mentioned it already, we will rule out that MJ will be larger than MK because of the fact that the 2 athletes will be modeled symmetrically. So Lazear, Rosen, they assume that the error terms of the production functions are normally distributed, and therefore the density of bad luck, which is the difference between two error terms, is then normally distributed with a variance of 2 times the variance of the error terms. So the probability is given by the expected value of this difference is equal to 0, but it is 2 times the variance. Also, this is a small detail, and later on it will not pop up anymore. So, slide number 90, we arrive at another important assumption, that the two players are symmetric, and therefore in the equilibrium, the effort levels will be the same, mj equal to mk equal to m star. Yeah, let's think about the utility function once more. Utility function is given by equation number 12. So utility is given by the probability of winning, PM, and then W1 minus W2, staggering of prize money. So the structure of the prize money plus W2 minus the cost of excelling effort. So what we can see here already is that to some extent, the purse, like the sum of the prize money, will not be important. So W1 plus W2 does not pop up. Also, W2 will not play like a role in itself, because when we compute the first derivative, this part will be gone. So the difference between W1 and W2 will be important, but W2 itself will be not important, because you don't run when W2 is high or low or whatever. You are not motivated by W2, but you are motivated by the difference between W1 and W2. So let's take the derivative of this utility function with respect to m. We get, when we differentiate this one with respect to m, we get this g function times W1 minus W2, and then the derivative of the cost function with respect to m. This derivative has to be set equal to 0. And hence, we get like this first order condition of displayed in equation 14, when we put minus del C del M on the right-hand side of this equation, we get to this first order condition. So the marginal cost of effort, right-hand side of this equation, must be equal to the spread W1 minus W2 times the height of the density function of this probability function. So at the size of when x is equal to 0, like there only the height of this density function plays a role. In the paper, they say that the optimal effort level depends on the spread and the distribution of errors. And they also highlight that the optimal effort does not depend on the sum of the prices. The optimal effort does not depend on the purse, the sum of the prize money, die Summe aller Preisgelder, W1 plus W2 does not pop up in this first order condition. So this is the interpretation in the article, but I think that this is different. So when I look at it, especially later on in our numerical example, I don't think that the optimal effort depends on the spread and the distribution of errors. I think it's the other way around. So I think that the optimal spread depends on the distribution of errors and the optimal effort. So of course, like we have one equation here, but how this relationship is interpreted, we can look at it from two different angles. The paper is one view, and I think I'm right, but we'll find out later on, or at least I think that you will understand my point. So we are switching to a different subchapter. You can always see the subchapters in the left upper part of the slide. So I will talk about the participation constraint now. Participation constraint deals with the question, are the agents joining the tournament? Do the athletes show up at the starting line, and do they start to compete? So until now, we learned that staggering of the prize money is very important. So right now, we think that only the difference between W1 and W2 is important. And we have seen here like two scenarios, scenario A and scenario B. And in both scenarios, the staggering of the prize money is equal to 40. What if one very intelligent tournament organizer is telling you, hey, in case that this difference, that only this difference is important, then let's say that W1 is equal to -10, W2 is equal to -50, then it's also the case that W1 is larger than W2, and also the difference between W1 and W2 is equal to 40, then I should get the same result in C as I get in A and B. But this is not the case due to the so-called participation constraint. The purse, like die Summe aller Preisgelder, will determine whether the worker will play the game. In the principal agent literature, this is called like the participation constraint. And we will determine the participation constraint by looking at equation 15. Since both workers excel the same amount of effort, and when we take additionally the information about the error structure into consideration, then the equilibrium will be symmetric. And this implies that each worker will win the tournament with a 50% chance, and a worker, the athlete, will only join the competition if 1/2 times the purse is larger than the cost. Why 1/2 of the purse? Because with a 50% probability, I'll be on place number 1. With 50% of the probability, I'm on place number 2. So, like my expected payoff is like 1/2 times W1 plus 1/2 times W2. And then I also have the cost. I have to take the cost into consideration, the cost of running and competing, the cost which are created by the effort level. And this has to be larger or equal to 0. When this relationship is equal to 0, we still sign the contract. When it's larger than 0, then the agent will get like a positive payoff, a positive utility from this race. Okay, what about the firm? The workers, the athletes, optimize subject to the constraints imposed on them by the firm. The firm still writes the contract. The firm is in control of the purse and the price spread. And in the tournament setting, it adjusts these two elements in order to maximize profits. However, the forces of competition limit the firm in the dimension of both purse and spread. It is very important that we remember that the firms, the tournament organizer, are operating in the market structure of perfect competition, so that the tournament organizer in the end will not make a profit. I'll come back to that in about 2 slides. Let's once more think about the profit function of the firm. The output of the firm is on average given by the sum of the effort levels, the sum of effort excelled by athlete J plus the effort excelled by player K, because of the fact that the error terms do not matter. The output can be sold at the price of V. Profit is defined by revenues minus cost. So the expected profit is, of course, like QJ plus QK times V. But when we take the expectations, then the error term, which are still included in QJ and QK, will drop out, and we end up here at the optimal effort levels in the revenue part. And the tournament organizer is paying like W1 and W2. So this is the profit of the company. Competition drives down the profits to the level of 0. So we can also consider the 0 profit condition here, that revenues have to be equal to the cost. When revenues are equal to the cost, then it is the case that the profit to the firm will be equal to 0. Since the 2 athletes are modeled in a symmetric way, MJ is equal to MK is equal to M, we can also modify the right-hand side in a way that instead of this bracket, we plug in 2M times V in the profit function of the firm. Okay, the firm maximizes the payoff for the worker. This is also like a very important assumption which is made in this paper. It is the case that the firm has to make the right choice in terms of the spread of the prices in order to achieve 0 profits, and on top, in order to contract the 2 athletes and motivate the athletes in a way that they really show up at the starting line and that they answer with a positive effort level. The wrong choice would mean that the firm will experience losses. They will not break even, but will make a loss. So competition will limit the behavior of the firm, and in order to attract the workers, the firm has to offer a spread for any given price which maximizes the worker returns. Thus, the firm's behavior is aligned with the worker's interest by competition. So the firm has to choose the spread in a way that it maximizes the expected earnings to the worker. So once more, the principal has to put himself into the shoes of the agents, has to maximize the utility of the agents in order to learn the here, not participation constraint, but the Benti, the other constraint. Sagen Sie mal eben, Participation. Anreizbedingung. Benti, sagen Sie mal eben. Incentive Constraint. Oder wollten Sie gerade sagen, ne?
Ja.
Ja. Okay, ich fange nochmal an. So, like, the principal has to put himself into the shoes of the agent, has to maximize the utility of the agent in order to learn the incentive constraint. And then the principal will use the incentive constraint in his calculations. Okay, the firm has to maximize the payoff for the workers. This is the utility function. We plug in that the probabilities are 0.5. We can write 0.5 out of brackets and we get to equation number 20. Now we can consider the zero profit condition in this relationship. We have W1 plus W2 is equal to 2 times MV from the zero profit condition. When we put the 2 on the other hand side of the zero profit condition, we get to this relationship here. So this relationship highlighted in blue is still the zero profit condition of the firm. We put the 2 on the other hand side, and then we get to this expression here. And then it is the case that we can combine the utility function and the zero profit condition. And we can put M star V and insert this into the utility function. So we take the zero profit condition and insert this stuff into this part. Then we get to this utility function, and we can differentiate this utility function with respect to the spread W1 minus W2, and we get V times del M del W1 minus W2 minus del C del M del W1 W2 has to be equal to 0. We can write this stuff out of brackets. So this one and this one out of brackets, or we put this one and this one in brackets, and we write del M del W1 minus W2 out of brackets. And we get to equation 23. So this one and that one combined, and then in brackets V minus del C del M star. The second term, like this one, is always positive. Why is this stuff always positive? This is always positive because of the fact that the two athletes always assume that W2 is like a basic weight rate. W2 is a basic weight rate and it has no impact on the effort level. I'm only starting to compete. I'm starting to compete for the difference W1 minus W2. I'm only starting to answer with an optimal effort level in case that the spread is positive. And the higher the spread, the more to gain in the competition. So the higher the spread, the higher the effort level, and the blue stuff will always be positive. Therefore, it is the case that this first order condition given in equation 23 can only be met in case that V is equal to del C del M. So the first term, the term in brackets, has to be equal to 0. And to some extent, we have seen equation 24 before. V is equal to del C del M. Where have we seen this stuff before? Let's check. Here, like slide number 12, V is equal to del C del M. When we talked about the accord loan piece rate compensation, there we also get to know this relationship here. So the once more, when it comes to this competition, it is the case that the optimal effort level is determined by a V. This is a price the spectator will pay for the competition. This will affect in the end how large M is. And hence, like Lazear and Rosen have shown here, that setting up a competition is as efficient as, like this piece rate work or piece rate compensation. Setting up this kind of competition is as efficient as an accord loan. So we have seen this kind of stuff already. V is equal del C del M star. Great. I believe that nobody has a question here. So let's summarize the three most important equations of this paper. The first one, staggering of the price money times the height of this density function is equal to del C del M. This stems from this equation here, differentiating the utility function with respect to M. Then the next important equation, W1 plus W2 is equal to 2mv. This is a zero profit condition. Zero profit condition, the firm is operating in the market structure of perfect competition, therefore zero profit. And the last one, this stems from that the firm is optimizing the optimal staggering of the price money. So the difference between W1 and W2 is optimized by the firm, so that this difference W1 minus W2 is maximizing the utility for the athletes, so that the utility of the athletes becomes optimal. So the first one is optimal utility with respect to the effort level. The third one, optimal utility with respect to staggering of the price money. And the equation in the middle is a zero profit condition of the firm. So sorry, like I talked 1 hour, and all that matters is summarized on this slide. This will solve the underlying problem. Great. Numerical example. Let's assume V is equal to 15. So V is exogenous. V equal to 15. This is the amount of money like the spectator is going to pay for watching the sports competition. V is equal to 15. And G is the height of this probability function. G is equal to 0.5. So we have talked so much about this probability function. In the end, it is just a number. And the cost function is given by C equal to m to the power of 1.5. So we know already the characteristics of this cost function. So we want to find the optimal structure with respect to W1 and W2. And we also want to know like how much effort is excelled, and the whole problem should be solved here. So in a first step, we can use this optimality condition, which is on slide number 29, equation number 3, to compute the optimal effort level m star. So V equal to the first derivative of the cost function with respect to m is equal to V equal to 1.5 times m to the power of 0.5. Let's solve this stuff in order to solve for m. We put the 1.5 on the other hand side of the equation, pops up in the denominator, and afterwards we square the whole stuff so that m is isolated on one hand side of the equation. We get that m is equal to v over 1.5 squared. When we plug in v, we get to this relationship here, that m is equal to like 100. So the optimal effort level is equal to 100. Step 2. We use W1 plus W2 is equal to 2 times m times v. This is the zero profit condition of the firm in order to compute the optimal purse. So we know already, we know the two, we know m is equal to 100 and we know v. And then when we plug in the information we have, when we plug in the 100 for the effort level and the v equal to 15, we know that the purse is equal to 3,000. So W1 plus W2 is equal to 3,000. Step 3. We use W1 minus W2 times G is equal to marginal cost of the worker in order to compute the spread. So when we put G on the other hand side of the equation, we get W1 minus W2 is equal to C prime over G. This is once more equal to 1.5, the 100 for m to the power of 0.5, like the first derivative of the cost function with respect to m, and we plug in m here. Divided by G is equal to 0.5. So we get, this is equal to 10. 10 times 1.5 is equal to 15. 15 divided by 0.5 is equal to 30. So the optimal spread is equal to 30. Step 4. We use W1 plus W2 is equal to 3,000 and W1 minus W2 is equal to 30 in order to compute W1 and W2. So, we can subtract this one from that one. When we say this equation minus that equation, we get W1 minus W1. W1 is gone. W2 minus W2 will be 2 W2s. And then we have 3,000 here and minus 30 there. So that's here Gauss algorithm. This one minus that one gives you this one. Then when we solve for W2, we get W2 is 1,485. And when we plug in this stuff into this definition here, W1 plus W2 is equal to 3,000. And we put W2 on the right-hand side, we get to equation 28. W1 is equal to 3,000 minus W2. And then we get W1 is equal to 1,515. These are the optimal W's. The spread is equal to 30. So when you subtract 1,515 minus this one, you get to 30. The purse is equal to 3,000. And the optimal level of M is equal to like 100. Okay, I'll switch to the main